Alright, so here's Joe's in lab. And here's our AM radio receiver. And Joe's just plugged in the amplified speaker to the output of our diode rectifier. And then you see on the oscilloscope, you can see that we're clearly hearing with the yellow trace on the oscilloscope. You can see the correlation between the radio sounds and the motion on the oscilloscope. Okay, now let's back up a little bit. And first, we have an antenna coming in the window. This is basically just a piece of wire going out to that tree over there. You can kind of see the wire hang. So it's not an ideal antenna, but anyway, there it is. Here's my little sign. It says Physics 364 antenna. And it turns out, well, okay, I guess you can hold the camera. So it turns out, if we just take the antenna and send the antenna straight into the oscilloscope, and then we're going to go to a reasonable time scale for the antenna, which is megahertz. So here's like 1 microsecond time scale. Then we move this trace down, and we move the trigger up. Oh, we'll get some fuzz here. So here, if I just stop it, we look at one trace. Then see, this is a microsecond per division, and you can see there's a lot of fast structure from high frequency stuff, but you can see that something around a megahertz is kind of dominant. Now we run this thing again. Now we've got now I've got this thing going into an op-amp charge current to voltage amplifier because this is a current source. So I plug Mr. Antenna, which is a current source, into this op-amp charge to voltage amplifier. And then I look at the output of this op-amp circuit with this scope probe here. So here's the output. This is just an ordinary op-amp, but it's an AD847, which has 50 megahertz of bandwidth, which is a little bit more suitable for this application than the 5 megahertz bandwidth. Oh my gosh, so look at the size of this thing on the scope now. You saw how small it was before. Now we have to zoom out on the vertical scale. Okay. So now this is 2 volts per division. So we've got a huge signal here. If we just stop it, okay, so then this is pretty big. And now if we get the voltage trace out of the way, and we look at the Fourier transform of the voltage trace, let's see, oh yeah, so let's move to a broader time scale here. So now I'm moving to 20 microseconds per division, and then the red trace is the Fourier transform, and I can move this cursor around. So you can see as I move this cursor, the strongest AM station you see is 950 kilohertz. I can move it a little bit to the right, and I see 990 kilohertz. I move it a little bit farther to the right, and I see 1060 kilohertz. And I move it even farther to the right, and I see 1210 kilohertz. And here, let's go to the left a little bit, and I see 800 kilohertz, that's 800 AM. And then back a little bit, there's 700 kilohertz. Oh no, it disappeared. I don't know what's happening there. That might not be a real station. Okay, then this is 610 kilohertz. So now we're really toward the left-hand side of the AM dial. That's 560. Anyway, so here's 950 kilohertz. Okay, so then the next trick is to make a bandpass filter which picks out that frequency and sort of suppresses other frequencies. And Joe's has done that here. So if we look at the output of the bandpass filter, so it's an RLC bandpass filter, then what we see, well actually here's the output of the bandpass filter, and it doesn't look all that different because it's not terribly selective. If we actually increase this resistor by an order of magnitude, there we go. Here's a nice big resistor. So if we increase this resistor by about an order of magnitude, then you should see a much more selective bandpass filter. Yeah, see, so now you've really gotten rid of a lot of the shoulder and sort of enhanced this one peak around 950 kilohertz. And I guess, you know, we could, with an even higher Q in principle, we could even filter out these two neighboring stations, but it turns out just this is so much stronger than the neighboring stations, you don't really have to do that. In fact, we don't even have to do really what we did already. We can lower the Q a little bit. Now Joe's going to start to hate this because I'm just kind of being vague, but okay, I reduced the Q even further because it turns out that it's
get a bigger signal.
Too big a resistance makes the signal too small because of losses in this inductor, in this RLC circuit. Okay, now are we going to show you how it rectifies? We have this little diode resistor capacitor circuit whose purpose is to rectify. So in other words, we've got this 950 kilohertz sine wave, and then to get the information out of it, we want to have a circuit which remembers the most recent peak. So you can make with a diode and a capacitor and a resistor effectively a peak detector. Well, with a diode and a capacitor you can make a peak detector, or with a diode and a resistor you can make a rectifier that just takes the positive part of the waveform. But it turns out if you have a diode and a capacitor, charge flows through the diode into the capacitor when the incoming signal is bigger than what's on the capacitor. So you remember the most recent peak. And then the resistor drains the charge. And if you choose the RC time constant to be longer than the information content is kind of kilohertz, that's milliseconds, but shorter than the, choose the RC time constant to be short enough that
the carrier frequency.
Yeah, so you want the time constant to be much longer than this microsecond carrier frequency and much shorter than the millisecond information frequency. Okay, I didn't say that very well, sorry. Okay, so then that is our rectifier, and I think we can even probe the output of the rectifier with the scope probe. Let's see if that works. Okay, so now this is a considerably smaller signal because we pay the price of the diode drop. So let's move this down to where we can see it. And then this is 20 microsecond time scale, so we want to go out to a kind of millisecondish time scale to see audio frequencies, and then we want to zoom in to be able to see small signals. This is 200 millivolts per division. So now you can clearly see activity here. So basically the rectifier, why is it picking out a negative signal? Oh, it's picking out a negative signal because the diode is plugged in backwards. So if we reverse the diode, somehow the diode got plugged in backwards. If we reverse the diode, then we should see a positive signal. Okay, there we go. So there's a positive signal. There's our information. And it looks as if the amplitude of the modulation that we can see is about 200 millivolts. So then we plug that again into the amplified speaker. And there you go. We're listening to WPEN AM 950.